them together, and then you'll do the others on your own. Let's say I do. Did we do this one already?
No.
Okay, cool. If you would, let's consider that. Now, first, if I were to place this point, then actually take it back. That one's an easier one. Let's do a harder one, shall we? Let's do this one. Okay? Now, I remind you that the R comes first and the angle comes second. And although the angle comes second, you actually do the angle part first. So you're going to start at the positive x-axis. If the angle is positive, then you turn up from the x-axis. And 7 pi over 4 is here. Yeah? Oh yeah, I said this was a negative. So would you throw a negative on there? Okay, thank you. Now let's change it. That makes it harder. So I'm going to start at the positive x-axis. But if the angle is negative, then I'm going to turn down this way. And if I go 7 pi over 4 in a negative direction, where does that put me? A normal pi over 4. Okay, now every negative angle and a positive angle together make 2 pi. So if the negative angle is 7 pi over 4, then the positive angle must be 2 pi minus that 7 pi over 4, so pi over 4. So at the end of the day, we're going to face, now we're just at the origin still. We're still at the origin, and I'm facing this direction. But I'm looking that way, but the fact that this is negative 2 tells me don't go forward 2, I go backward 2, and so that puts me actually in the third quadrant. That is where that point is. You see where I'm coming from? Okay, I know it's kind of wacky, but you'll get used to it, and it'll get easier and easier. Yes?
So do the circles kind of inside the circles represent like 1, 2, 3?
Yes, exactly. The circles, it's not like X and Y still aren't there. It's just in order to get 2 units out from the origin in any direction, circles are better than grid. So yes, each circle is 1 unit, yes. Unless otherwise told. Okay, so I'm trying to get there in lots of different ways. One way we did this was to turn a negative angle and back up 2. Let's go to this one. Now this one is to turn a positive angle and back up 2. What would that be? Pi over 4 is the positive angle you can turn, but because we're backing up, it's still a negative 2 there. Okay? Now those are the 2 possibilities for facing the opposite direction. Pi over 4 and negative 7 pi over 4. You done?
Yeah.
Okay. Now let's look at the 2 possibilities of instead of facing the opposite direction, which is crazy, actually face the direction you want to go. So let's talk about the 2 ways to go forward 2 units. Now if I'm going facing the correct direction and going forward 2 units, then that means a positive 2 in R, or distance. I'm traveling as positive and I'm going forward. We cool? Yeah. To face this direction, I could do 2 different angles. A positive angle where I turned up, or a negative angle where I turned down. This column 3 is the negative angle. What's the negative angle I turned? Negative 3 pi over 4. Do you all see where that's coming from? Okay? Yes? Just stretch it. Okay. Positive angle. 5 pi over 4, 7 pi over 4?
5 pi over 4.
They should add the 2 pi, so it's 5 pi over 4, and that's positive. Very cool. Okay? Now, the rectangular for this goes to a little bit of trick here. If I said, hey, here's the 45-degree angle, and I want the x and the y, I think we can all agree that in the third quadrant they're definitely going to both be negative. How do I find the x and the y? Think of it like normal pi over 4. A unit circle, the radius is 1, right? But here I'm going out 2, so it's everything multiplied by a factor of 2. So it's cosine of that angle, but times 2. Root 2, right? Because negative root 2, because it would have been root 2 over 2 for the cosine, but multiplied by 2, we get negative root 2. You follow me? Okay. And what about the y? It's also root 2. Okay. Would you like to try one on your own, or just move on?
No, let's do it on our own.
Okay. Have we done this one?
Nope.
Okay. Try this. Try that row, please.
Because we're doing the radius is 2 times.
Ready? Okay. Cindy, what do you think for the rectangular part of it? What did you say? 0.4, did you say?
Yeah.
Okay, I agree. What about the positive r, positive theta? I'm just mentally thinking. 4 pi over 2, I agree. They gave us positive r, negative theta. Let's jump to negative r, negative theta. What do you think? Brown boys together in unison.
Negative 2. Okay, negative 4, comma, negative pi over 2.
Positive. It's positive. You said the last.
Oh, you want that column?
Oh, sorry, that's you give me this column, yeah?
But it's 3 pi over 2.
Okay, positive 3 pi. Okay. Yeah, I was just about to have Ben and everybody else go together. All right, are we good? Okay,
They can do better than us.
now, oops. This lesson is a lot in one, so stick with me and we'll practice it. But you need to be able to jump from not just one point to the other form, but equation to other form, okay? So if you just memorize a few, actually, if you just understand this picture, then you don't have to memorize anything. To get to any point in space, if you draw a triangle, in that triangle you will see x, y, theta, and r all together. And just by understanding math, which you do, you should be able from that picture to see lots of relationships between x and y and r and theta. Give me one x, y, r relationship or x, y, theta relationship. X squared plus y squared is r squared. Or if you like, r is technically plus or minus, but we typically use plus the square root of x squared plus y squared. That's one relationship that we could use to jump from one form to the other, okay? What about, give me a y, r, theta relationship, please. Sine theta is y over r. It's more common that you say, therefore, y is
Inverse sine.
r sine theta,
Yeah.
right? And therefore, by the same kind of thinking, but skipping that step, x is r cosine theta. You with me? That makes sense. X is always like cosine, and then you're stretching it by a scale factor. That's what the r does. You're just amplifying it. It's a scale factor. Okay, and what about the theta xy relationship? Inverse tangent of
Y over X.
y over x equals theta. So, with those, I'll call them 4 facts, you can make jumps from one equation form to the other. For example, y equals 2x plus 3. What can you put in y's place? R sine theta. What can you put in x's place? R cosine theta. Now, we've converted that. When I say convert that, I mean take it from xy, or rectangular, to r theta, or polar. It's more common that you solve this for r. How would you solve this for r? Move the cosine over. I'm with you. And then factor and divide. So you would say that the equivalent form of this is r is sine theta minus 2 cosine theta. Okay? All right. R equals 3 cosine theta. What can we put in r's place? Actually, so this is get a bit of a trick to it. You want to be smart here now. I could put in square root of x squared plus y squared. And cosine isn't perfect. Cosine's not great because I would like there to be an r here. Love there to have an r. Yeah? Well, multiply by 1. Make 1. If I multiply both sides by r, oops, that helps me a lot because on the left side I have r squared, which is nice, and the right side is 2 or 3 r cosine theta, which means that r squared is x squared plus y squared, and the other side is just x. Now, that's actually a circle, and we'll talk about that in a second. But for now, we'll just call it this. You with me? I went to x and y. I'm technically done. You good? Okay. Again, it says all that. All right. Now, different families of graphs. I have no doubt that when I tell you y equals 3x plus 2, you know what that graph is. You know it's a line. You need to have familiarity with polar equations and what their graphs are. So that's the rest of the day, is trying to get some familiarity with common polar graphs. There are 3 common forms of a circle. One is r equals, let's just go r equals 2.
Says R equals 3.
Oh, it already says, oh, my bad. R equals 3?
Yeah.
Okay. R equals 3. What does this one say? And this?
R equals
20 sine of theta? Okay. All right, cool. All right. Now, back in the day, you probably never had trouble with this, but the average Algebra 1 student has a dickens of a time with this graph. Y equals 3. Because there's no x, and they don't know what to do. And they say, what's x? I don't know what to make x. And your answer is x can be whatever it wants. When x is 5, y is 3. When x is 10, y is 3. Doesn't matter what x is, y is always 3. Now that freedom, like I said, is confusing to some students, but it's actually a very easy thing. Here, because r is set to 3 and there's no mention of theta, theta can be anything. So I can turn towards 0 radians, and r is 3. I can turn towards 5 or 6 radians, and r is 3. I can turn whatever way I want, and r is always 3. And so you get a circle, symmetric at the origin, with an r of 3. Go figure. All right. So the first form is r equals a, where a is a constant. It's centered at the origin, and the radius obviously is A, or whatever the number is they threw there. You down? What if it said R is negative 2?
Flip it inside out.
See,
It's
when
the
you
same
face
thing.
this angle, you go
Backwards.
back 2. And you face this angle, you go back 2. So R equals negative 2 would be exactly the same as R equals positive. Okay? R equals 4 cosine theta. Now you need to, yes, sorry.
So that means that the radius is the absolute value of A?
Yes. Yes. Maybe I should say the radius is the absolute value. Very good question. Good call. Okay. Now, you're going to start to get into a totally different mindset in polar. In rectangular, you think, okay, as I do this in x, y is this, and then so it's all about as I go right, I go up this much, because x and y are types of change. In polar, it's not about that. It's about as you turn, how far you go depends, all right? So here, this is your kind of school of thought. Cosine is limited, right? What's the most cosine can be?
1,
1. So the furthest you'll ever go from the origin is
4.
4, okay? Likewise, cosine gets bigger and smaller, bigger and smaller. So you're going to go out a ways and then get closer and closer to the origin, and can then you eventually be an R of 0? Does cosine ever equal 0?
Yes.
And in that case, you won't go anywhere, just be at the origin, and then you'll go backwards some, and then forward some, and backwards some. So you'll start to get a different thought process. But for the first time only, we'll do some actual points to see how this works. When theta is 0, what's R? 4. When theta, oh, actually, would you put up here, root 3 is about 1.8, and root 2 is about 1.4. Those will come in handy. Okay, so at pi over 6, when theta is pi over 6, what's R? Root 3 over 2 times 4, so 2 root 3. Now that's about 2 times 1.8, or 3.6-ish. So forward 1, 2, 3, and a little less. All right. So you can see that we were actually going out the very furthest at that first point, and now we're starting to go less and less far out. At pi over 4, R is 4 times root 2 over 2, or 2 times root 2, which is 2.8. 1, 2, and not quite 3 rings out. Okay? Now, connect as you go. We're saying this. We're going out further and further, but as we turn, we're going out less and less far out. At pi over 3, what's R? 4 times a half, so 2, yeah? And what about at pi over 2? R is? What's cosine of pi over 2? 0. Now if I go 0, that means I'm actually not going forward at all. That's just rough. So I'm at the origin. You with me? Okay. In this quadrant, what's the sign of cosine? At angles from pi over 2 to pi, what is cosine? Positive, negative? Negative. Now, if those are negative cosines, then I'll get negative r's. And if I get negative r's, instead of going forward, I'll go back. So as I face angles in this quadrant, I won't actually be going into the second quadrant. I'll actually be going into the fourth quadrant, because I'm going to be backing up, right? So at 2 pi over 3, what's the cosine of 2 pi over 3? Negative 1/2 times 4 is negative 2. So when I face this angle, I'm still at the origin now. I'm at the origin, but I'm going to face that angle and go backwards 2. And that actually sends me there. And that means that if you connect the dots, that is something like that, yay? At 3 pi over 4, cosine is negative root 2 over 2 times 4 is negative 2 root 2. If root 2 is 1.4, then 2 root 2 is 2.8. So negative 2.8. Now I'm going to face that angle and go backwards 2.8. Oops, that should be here. You cool? And then at 5 pi over 6. Cosine's normally negative root 3 over 2 times 4 is negative 2 root 3. If root 3 is 1.8, then 2 root 3 is negative 3.6. So back up 1, 2, 3.6. And then what about at pi? Negative 4, so I'll go back to my original point, yeah? Now, I can tell you, you can keep doing angles in here. If you do angles in these quadrants, you will get the same circle on top of itself. You're going to get negatives, which will back you up into the first quadrant. Here, though, they'll be positive, and you'll be going forward into the fourth quadrant. So R equals A cosine theta. Generally speaking, not 4 cosine theta, this specific problem, but generally speaking, R equal A cosine theta is a circle. Symmetric at the x-axis with a diameter equal to A. Now, what if I had R equal negative 4 cosine theta? Yeah, when theta is 0, you'd actually get a negative 4. You would start getting points here, and it would be over here. So if you get R equal a negative A cosine theta, it's on the negative x. You with me? Are you with me? Okay. By the same kind of token then, sine. Now sine is probably going to be a little different because sine and cosine behave differently. First and foremost, what's the max R I'm going to get? 20. So I probably will need to change my scale. Instead of going by ones, let's go by 10. 5. Let's go by 5 in order to get a good size picture. Okay? Okay. So let's start at theta equals 0. When theta equals 0, R is 0. So I'm starting at the origin. When theta is pi over 6, what's cosine, what's sine of pi over 6? 1 half, and 10 times 20 is 10. All right, so you're already headed out to 10, which is 2 rings out. What about at pi over 4? Sine is root 2 over 2 times 20 is 10 root 2. So it's about 14. 5, 10, 14 is just shy of 3 rings. Do you agree? Just shy of 15. What about at pi over 3? 20 root 3 over 2, yeah? So 10 root 3. 10 root 3 is 18, which is just shy of 4 rings. And then what about at pi over 2? 20. So this is a circle, and you can continue, but you'll see that that's a circle at the y-axis. R equals a sine theta is a circle with symmetry at the y-axis. Thankfully, that is totally in line with what we've always done. Cosine is x, sine is y, and the diameter is a. And again, have somewhere in your notes, if you have R equals negative a cosine theta, it's on the negative x-axis, and R equal negative a sine theta is on the negative y-axis. Follow? Okay. All right. Okay, now, the next idea is spirals. Does it say what to graph here?
No.
It doesn't? Okay, so r equals theta. It is. Taking, it says spiral, so I kind of ruined it. This will make sense that it's a spiral because the more you turn, r is directly related. So if you turn a lot, you go forward a lot. And the more you turn, the further out you go. When theta is 0, r is 0. When theta is pi over 6, r is pi over 6. Now, it's hard to go pi over 6 in terms of rings. So pi over 6 is about a half, yeah?
Yes.
Pi over 6 is about 3.14 over 6, or about a half. So go forward a half a unit. Pi over 4 is roughly 3/4, yeah? Pi over 3 is roughly 1-ish, wouldn't you say?
Yes.
Pi over 2 is 3 over 2-ish, so 1.5-ish. Now would you write yourself a note? For spirals, I want accuracy at the axes. Points. I don't require that you show me all the in-between points. So let's jump to pi. When you face pi, you go forward. Pi. So 1, 2, 3, maybe a little more because pi is 3.14, yeah? At 3 pi over 2. That's 9.5-ish, yeah? 4.5-ish. Down? 1, 2, 3, 4. At that point, I'm off the graph. You should go until you're off the graph. Off the space provided. Okay, what's this one? Does this have something? No. Okay, would you give me here that r is theta over pi? Now that seems complicated, but it's actually wonderful. That makes your life a lot easier. When theta is 0, r is 0. When theta is pi over 2, r is
2 over 2.
Pi over 2 over pi is
1/2.
1/2. Okay? At pi, r is 1. At 3 pi over 2, r is 3/2. At 2 pi, r is 2. At 5 pi over 2, 2.5. So you can see the pattern. 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. Your last point on the space provided should be at the positive x-axis when you hit r equal 4. Cool? Now this graph, if nothing else, is a good illustration of why polar is necessary. Can you imagine trying to write the equation for that using x and y?
Yes.
It's really difficult. Yes. Okay. Now, oops, darn it, I should clear these out. Graphing lines. Theta equal some constant. Constant is a line through the origin. Is a line through the origin. For example, if you said graph the polar graph of theta equals pi over 6, all that's required of me is that I face pi over 6. What is not defined is how far I go. So can I face pi over 6 and not go anywhere? Yes. Can I face pi over 6 and go 1? 2? 3? So this is a ray, yes? No, it's not Mr. Ray, it's Mr. Line. Because R can also be negative. And so it is a line. As the title indicates, it says graph line, not graph rays, baby. So come on now. All right, so what if I said graph theta equal 7 pi over 3. That's so gross. Why did I do that? Oh well. 7 pi over 3 is the same as
Pi over 3.
pi over 3. So isn't that just like that? Okay, cool. Is that all? Is that all?
That is all.
All right. Now, the homework should be doable. Now that we have those, the ones that you skipped are doable. So let's go to set 107. Number 9, 10, 14. Let's see. Okay, so 9 y equals 2x squared. Put it into polar. If you get stuck or you don't remember, remember this picture for your substitution facts. What's y equal to? R sine theta. What's x equal to? R cosine theta. Let's now solve this for r. Typically, we will solve this for r in most cases. So this is r sine theta equals 2r squared cosine squared theta. Yay? Now, I know it's going to feel like you're dividing, you're going to break math because you've been taught well. But dividing out an r, is this okay? I thought that was a no. We never divide out a variable. Okay, so you need to distinguish between these two problems. Okay? This is where you were taught, do not divide that x out. You will lose a solution. If you divide an x out, you say that x is 1. And you were taught properly that that's a bad math approach. You don't do it that way. What is the appropriate way? Move everything over. You've been taught so well. Factor. And then solve. Now, the reason that you're taught to do it that way is because the x equals 0 solution is not lost. The difference in why this is okay here is that you're not solving this for r. You're trying to graph. And if you do dump this r and get sine theta is 2r cosine squared theta, and r is therefore sine over 2 cosine squared theta, r equals 0 is still there. It's not lost. It is still a point on the graph. It's not dumped. So that lost solution is actually not a lost solution because you're not solving the graph. Okay? So don't worry about it. It is okay in this case to dump an r, and that's how you're going to solve for r. Okay? All right, go on to 10. 10 is something else. R equals sine theta. Now, you could do this by substitution, but graphing is so much better. Now, we'll do it both ways so you can see where I'm coming from, and then in the future, you'll see why graphing is better. If you did this by substitution, this is kind of like the problem where I said you want to have r's on both sides, so this is not just sine theta, but r sine theta. Remember how we just said multiply through by an r because it helps you? Remember that 20 minutes ago? And that gets you r squared is r sine theta. What's the left side? Because it's r squared now, it's just normal. X squared plus y squared, and this is y. And I guess you're done, but it's ugly. And it was more work. And there's a little gotcha into it. But if you were to graph this, so much easier. What's the graph of this look like?
Circle.
It's a circle symmetric at the y-axis. Is the radius 1 or the diameter 1? Okay, so if this is 1, therefore the center is a half, can you just write the equation of that in rectangular based on what you see? X squared plus it shifted vertically, so y minus a half squared equals the radius squared, which is, oh, this is not going as well as I thought. 1/2 squared, yeah? Now, this and this, they're equivalent. If I multiplied the second one out, it would look like that first one. But the first one is not as clean as our solution. It's not a known graph, and it was more work. So if you know the graph, use the graph. That's my point. You down? Are you with me?
Yeah.
Okay. What else do we need to do? You said 14?
Heck, yeah.
Is 14 a new, it's replaced? Okay, okay. So 14. R equals -4 cosine theta. You should be able to do that in 3 seconds. Cosine is symmetric at the x-axis, but if it's negative, it's symmetric at the negative x-axis, then it's for the diameter or the radius. It's the diameter. So you should have a circle that looks like that. You good?
Okay, Mr. Rickman, if
Yep.
the circle doesn't quite look like a circle, is that okay?
It depends on if you want to succeed in my classroom.
What if I'm just not good at drawing?
You should better get out of compass, baby. All right, so what about r equals 2 over pi theta? What kind of graph is that if r and theta are directly related? Spiral. As theta changes, r changes. The more you turn, the further out you go, you're spiraling out. It should be accurate at the axes. I'll give you a second to think that through. You do not have to put angles between 0 and 90 and just at the 90s, or the quadrangles they're called. Okay, so in order, your radii start at 0 and then go up by 1. 1, 2, 3. I don't know how many rings did I give you? 4. So by 4 you should be off the graph. Yeah? Okay. What about the third one? Circle. Centered where? At the origin. Okay. And what about theta equals 3 pi over 4? What kind of graph is that? It's a line, like a line or a line?
It is a line.
Oh, it is a line. And so it goes in the direction of?
Two Mr. Rays.
Yes, it's 2 Mr. Rays, or Mr. Ray back to back with himself, whatever you want to say. And there you go. Okay. Any other questions on 107? You don't have 106, right? You have 107. Okay, 107 questions. Hit me. 23. 6. 23 and 6. 23 replaced or straight up? I hope so.
Yeah, and I'm going up not to notice.
Okay. 23. Oh, that's a humdinger. Oh, big question. This is hard.
No, it's not.
Okay, so
Wait, they start here.
Yes?
So for number 9, can we divide by r?
Okay. Good shit. Okay. So, would you agree that without any absolute value monkey business, you're talking this is the graph, yeah?
Yes.
All right. Now, this is not a huge, it's just kind of a once in a while gotcha question about absolute value. But absolute value on the x does not do that flipping thing that you're used to. It's not on f, it's on x. So thinking about this from the biggest perspective, the big ideas of absolute value are positives are unaffected, negatives are affected. In this case, it's on the x. So what happens to the positive x's? So that part will be unchanged, it'll look just like that. What is changed is negative x's. Negative x's behave or get made to be like. So what happens on the left? So when you put in, think about it, when you put in a -3, because the absolute value happens first, -3 gets made to +3, and therefore -3 will look just like 3. And so what happens to the graph? It's a mirror image. It looks just like that, yeah? All right. Now in terms of before we get to the derivative, let's do this in a piecewise way. We just said that for x is positive, the effect is absolutely nothing. It's just like normal x minus 3 squared plus 1, yeah? What about for x is negative? Would you write the equation of this left side parabola? The vertex is at -3, 1. So, x plus 3 squared plus 1. Okay? You know, technically what's going on here is it's the opposite of the x, and you're factoring out a negative, and then negative gets squared. That's really all that happened in that, but it's easier just to look at the graph and everything. Okay. Now that said, now that we have the function, now we can take the derivative. The derivative of that f of absolute value of x is also a piecewise graph. The left piece is 2 times x plus 3 to the first times 1, I suppose, and it's x less than, what about the derivative? Will it exist at 0?
No.
Why not?
Because it's sharp.
Sharp turn. Okay, so strictly less than 0, and the other derivative is 2. X minus 3 of the first, strictly greater than 0. F prime at 0 doesn't exist. Follow?
Yeah.
That was hard one. All right, 6. Question on 6. Is 6 still a question? Is that legit? Sketch graph for, I think I told you this, but I'm going to keep telling you this. Ignore Saxon's way of letting t be all reals. And instead, unless I otherwise say, use the assumption that time is greater than or equal to 0. That is far more common in all calc textbooks besides ours. That's what you need to get practice on, okay? So sometimes I'll try and remember to put it on the paper, but I'll probably forget. So just go with that assumption and ignore his answer a little bit, all right? So we have x equals 2t minus 3, and y equals t squared plus 2, and we're supposed to do a ton of stuff. We're supposed to eliminate the parameter, find dy dx, and sketch. Okay? What do you want to, if you sketch first, then you're going to have to probably make a table, which we can do. Or do you want to eliminate the parameter and look at the yx equation and graph from that? Graph from that. Okay, so if we graph from that, then this is, remember, eliminating the parameter is done differently when you have algebra versus trig. When it's algebra, you do it by substitution. So t is x plus 3 divided by 2. If you plug that in, then you get y is x plus 3 divided by 2, all squared plus 2. Well, y is 1/4 x plus 3 squared plus 2. You follow me? Rough that in. I think the graph is shifted left 3 and up 2. And it's a wide parabola, possibly. And that's the path. Now I have to do the parametric part. Where does it start? What direction does it move? Where does it not go? What about the domain here? If t is greater than or equal to 0, then what's x? If t is 0 and up, x is -3, right? Follow me? And, well, I guess we could do the y. What's the y? Y is going to be 0 plus 2 and up, so greater than or equal to 2. So in terms of graph, do we take the whole parabola or just piece? Just this piece, all right? And not that piece. Now you show time equals 0. So this is the first part. When you eliminate the parameter, you should have a domain and range hanging off it. You should show where the initial point is. At time 0, where did it start? At that vertex point, yeah? This was the starting point. And what direction did it go? Okay? Last thing we need to do is find dy dx. I don't care if you find dy dx in terms of x or t. If I found dy dx based on my eliminated the parameter form, what's dy dx? Derivative of this, 1/2 x plus 3. Do you follow? If you do it based on the t form, then dy dx is dy dt over dx dt. What's dy dt? 2t, and what's dx dt? 2. So dy dx is just t. That actually makes sense because t is x plus 3 over 2, and that's exactly the same. Right? We cool? Okay, what about 13? Do you need 13 still, my friend? 13. Find a generating formula for. Some people have a hard time getting. Oh, what the heck? They're starting at 2. That's so weird. They're starting at 2. That is practically never done, but whatever. 1 negative 8 ranks. 1 negative 32. This 64, 36. Oh, sorry. Sorry. Yeah, they do. You bet. And I do? Not do.
Not do.
Oh, I didn't know that. First problem, number 1 should have been parallel to the y-axis, not the
I'll just take the F.
I'm like, I would forget something.
Bye.
Oh, let me put my Tupperware away. It's finished my potatoes.